Hi everyone, my name is Lydia, and this is what I wish they had taught me about econometrics and introduction. Today we're continuing on our series on the CEF talk, and we're going to finally make its connection to the OLS. For most of you, the OLS is the term that it's mostly used whenever you're doing regressions, and the CEF is not even mentioned most of the time. So here we're going to talk about the best predictor and its best linear approximation, meaning the CEF and the OLS. Keep in mind, going forward, the CEF is the truth. The OLS is just the best straight line version of that truth. And the CEF is the real pattern that connects your y to your x. The thing is, we rarely know that function. So how do we estimate it? Well, that's exactly when the OLS steps in, because the OLS is the best linear approximation of that real pattern. Okay? Imagine that you have to guess y after seeing like x values among all possible guessing rules. And keep in mind, these guessing rules can be straight lines, they can be curves, they can be even squiggles. The one that will make the smallest average squared error is the CEF, or the conditional expectation, as we said. So the y conditional on x. So again, if we have x, which we can observe, and we have to guess y based on that, the best predictor would be the expectation of y conditional on x. This is the best possible predictor, okay? Math-wise, this we will also write it as the minimum, and most of the times you'll see that argument minimum. And the minimum will be based on the m here. I'll explain what it is, of the expectation of y minus some m function of the x all squared. Okay? So no other function will fit the data structure better, because it will capture every systematic part of y, leaving only that random noise which we talked about in the decomposition property of the CF. So let me show you visually what I mean by that. So if you notice figure 1 in here, we've got this data that looks very clearly like if we were to fit some sort of a line in here, would look very quadratic. Okay, so obviously, the CEF is the best at doing that, because while we can't fit a straight line, well, we can fit this kind of square looking or shape. In this other one, it can be even like the squiggly case that I told you. So these could be just simply something like that. Okay. In going back to the case where we do it like by finding the average for group by group, then this would have been all the averages, and we would have simply drawn the CF by connected all of these averages. And we can see here, it's not exactly linear. There are a few kinks in there, but that is what captures this data the best. Now, here's the problem. As I said, we don't know the true shape of these conditional expectation. It could bend, flatten, wiggle. So what if we actually restricted ourselves to a straight line? So among all the lines, we will find some line of the shape of alpha plus beta x, which will give me potentially this smallest average squared error we're talking about. Well, that line, the one that will basically, let's say, in parentheses, hug the true CF value as close as possible, is actually found by a problem that you have seen mathematically written as the minimization of the expectation of y minus alpha plus beta x all squared. Okay? So this is the solution to the population of the OLS line. Okay? This is the solution to that. Make the comparison with the CEF. The CEF, we have declared it as some function of x. So we have m of x. However, in the OLS, we are simply assuming it's a straight line. And the problem is the same. However, the function on which we apply it is slightly different. And that makes sort of also the connection between the CEF and the OLS. So the OLS is giving that linearity to my prediction. And the OLS is the best linear approximation. So going back to our graph in here, that if the data was slightly different, in here, if we had drawn the CEF, we'd just connected all of this. And as you can see in this case, it's quite linear. Well, that means that if I were to draw the OLS line in here, the OLS line in this case would have like perfectly matched the CEF line. I'm trying to show it as much as possible. However, in the case that it wasn't linear, you see the OLS would have been the one that bestly describes this relationship. Very clearly, it doesn't take all of the averages in here, but it's the best linear approximation that you can do. That's why for people who use the Angerstein-Pischke book, you'll see that the regression threads the CEF. So OLS, it's not claiming to be the best perfect linear line out there. It just finds the line that best summarizes the real and sometimes messy curve underneath. Going back to our metaphor, if econometrics is our Batman, so this a very misunderstood hero who's trying to make some sense of the chaos in the world, the CEF is the Batcave, meaning the hidden truth. The law of iterated expectation was Alfred, the guy who was keeping all the logic coherent throughout. The OLS is the Batmobile of your Batman, meaning your best linear ride through the messy streets of data. I hope this was helpful for you making the connection between the CEF and the OLS, because I know most of the times you only talk about the OLS. And we'll continue our next videos with a more fun elements to add to our econometrics work. See you in the next video.